Hello friends, welcome back. Last time the divergence theorem took us from local to global. Tiny sources summed inside a volume equal the flux through its skin. Today its twin sister and the last tool in our vector calculus box, Stokes Theorem. The statement, the circulation of A around a closed curve C equals the flux of the curl of A through any surface S that hangs on that curve. In symbols, the closed line integral of A dot dl equals the surface integral of curl A dot ds. Why does it work? It is the same trick as last time, one dimension down. Tile the surface into millions of tiny cells. Each cell carries its own tiny circulation, its curl times its area. Now add them all up. Every interior edge is walked twice, once by each neighboring cell in opposite directions, so those contributions cancel. The only edges that survive are the outer ones, and together they form exactly the boundary curve C. So the sum of all the tiny swirls equals one big walk around the rim. That is Stokes' theorem. And just as the divergence theorem handed us Gauss's law at the end of the last video, this theorem will hand us Ampère's law before this one ends. Worked example 1. A unit square. The field is the one we have carried since PS05. X squared y x hat plus y squared z y hat plus z squared x z hat. This time the region is not a volume but a surface. The unit square in the z equals 0 plane, x and y each from 0 to 1. Its boundary is the square's rim, and we will walk it counterclockwise. One bookkeeping rule before we compute, the right-hand rule. Curl the fingers of your right hand along the walking direction, counterclockwise. Your thumb points up, plus z hat. So the surface normal is z hat. Surface side first. The curl we do not even need to compute because PS06 already did. Curl of A equals minus y squared x hat minus z squared y hat minus x squared z hat. We only need the component along our normal, z hat, evaluated on the plane z equals 0, minus x squared. Integrate it over the square. Minus x squared dx from 0 to 1 gives minus 1/3. The y integral gives 1. Surface side, minus 1/3. Now the line side, 4 edges. First, a gift. The y component of A is y squared z, and on our plane z is 0. So a y vanishes everywhere on the square, and the two vertical edges, where we move along y, contribute nothing. The bottom edge, y equals 0, there ax is x squared times y, which is x squared times 0, 0 again. Everything hangs on the top edge. There y equals 1, so ax is x squared, and we walk from x equals 1 back to x equals 0 against the x direction. The integral of x squared from 1 to 0 is minus 1/3. Add the 4 edges, 0, 0, 0, minus 1/3. Line side, minus 1/3. Minus 1/3 equals minus 1/3, and savor that minus sign for a second. The curl points along minus z, while our walk circles the plus z way, so the circulation comes out negative. Even the sign agrees. The theorem is verified. Worked example 2. And just like last time, this is where the real lesson lives. Take the vortex field. A equals 1 over rho in the phi hat direction. In words, the field circles around the z-axis and it grows stronger as you approach the axis. Picture water swirling around a drain. Let C be a circle of radius r around the axis, and S the flat disk it bounds. Surface side first, naively. For an azimuthal field in cylindrical coordinates, the curl is 1 over rho times the partial derivative with respect to rho of rho times a phi in the z hat direction. But rho times a phi is rho times 1 over rho, just 1, a constant. Its derivative is 0. So away from the axis, the curl is exactly 0, and the naive surface integral gives 0. Hold that. Line side. On the circle of radius r, the field has magnitude 1 over r, and the path element is r d phi, pointing the same way. Multiply them. The r's cancel, leaving just d phi. Walk the full circle, phi from 0 to 2 pi. The circulation is 2 pi. Stop and feel the contradiction. Again, the surface side said 0. The line side said 2 pi. And notice something striking. The answer does not even depend on r. Any circle around the axis, big or small, gives exactly 2 pi. All the swirl is concentrated in one place, the axis itself, where the field blows up. Just like the point charge last time, the curl there is not 0, it is infinite, a two-dimensional delta function. Curl of phi hat over rho equals 2 pi times the two-dimensional delta of rho in z hat. Integrate that over the disk, and the surface side gives 2 pi as well. The theorem is restored once we are honest about the singularity. And now the payoff. Multiply the field by I over 2 pi. 1 over rho phi hat becomes I over 2 pi rho phi hat, and that is exactly the magnetic field H of a straight wire carrying current I. The circulation of H around any loop enclosing the wire becomes I, the enclosed current. That is Ampere's law. Ampere's law is Stokes' theorem applied to the vortex field, with the singularity, the wire itself, properly handled. Every Amperian loop calculation in magnetostatics rides on this. Quick recap. Stokes' theorem says the circulation of a vector field around a closed curve equals the flux of its curl through any surface spanning that curve. Local swirls, summed up, equal one walk around the rim. Two worked examples. First, the unit square with our running polynomial field. Surface side, minus 1/3. Line side, minus 1/3. Sine and all. A clean, no tricks verification. Second, the vortex field 1 over rho phi hat. The naive surface integral gave 0, the circulation gave 2 pi, and the mismatch was the whole point. The curl hides on the axis as a delta function. Scale by I over 2 pi, and out comes Ampere's law. The circulation of H equals the enclosed current. Now step back and look at what we have built across these 8 problem videos. Gradient, divergence, curl. Then the divergence theorem turned local sources into Gauss's law. And today, Stokes' theorem turned local swirls into Ampere's law. The vector calculus toolbox is complete. These two theorems are the bridges between Maxwell's differential and integral forms, and from here on, we will use them everywhere. See you in the next one.